Okay, so this is Brian O'Neill, and I'm going to show you how to solve 7.1. So it said from the above example, show that, um, man, I'm not quite sure how to name this one. Um, mu1 of set mu superscript 2 sub 1 is equal to, I probably should use my pencil to point. It's equal to mu superscript 2 sub 3 is equal to 0. Now, luckily, the example solved our eigenvalues for us. So we know that lambda sub 2 is equal to 5. What we need to do is we need to plug that back into this equation here, which is effectively our original matrix minus lambda on the diagonals. So previously, let's see, I think we must have started with 7, 5, and 4. And so 7 minus 5, 2, 5 minus 5 is 0, 4 minus 5, -1. The rest of it stays the same. Then we multiply it by mu superscript 2 sub 1, mu superscript 2 sub 2, and mu superscript 2 sub 3 to get our mu superscript 2 vector. So, oops, sorry, I bumped the camera. So if we plug that in for the first row here, we get 2 times mu sub 1. I want to skip the superscript part for now to make this video a little shorter. So we get mu sub 1 times 2 minus mu sub 2 times 0 minus 2 times mu sub 3, and that has to equal, we set that equal to 0. So from this first equation, I can see obviously that since we have the exact same we have coefficients in a negative, mu sub 1 superscript 2 is going to equal mu sub 3 superscript 2. So we've established that those are equal. So the first part of this equation is true. Now for the second part, we have another equation we can use to solve the last bit here. So we have -2 times mu sub 1 plus 0 times mu sub 2 minus 1 times mu sub 3. Well, since we know that these two are equal, then there is no other value except 0 for both of them that will satisfy the last equation. So we now know that the top equation is true.